Good morning. So far in the lectures we have been talking about properties of particles that are potentially of relevance in mechanical operations. We started discussing shape and size. In the last class we started to discuss about certain structural and interfacial properties of particles that could be of importance. So in terms of the structure of the particle, we said that can be segmented as three distinct regions: the core, the subsurface and the surface, and that the surface of the particle is what participates most extensively in terms of interactions with the surroundings. And then we identified certain interfacial properties that are of particular importance, and we discussed one of them in some detail, which is the surface energy, which for a particle again is the equivalent of surface tension for a liquid droplet, for example. So today we will discuss a couple more of these interfacial properties that are important, and then we will start discussing certain aspects of particle behavior in flow systems that again have a lot of relevance for mechanical operations. So the second property, interfacial property of a particle that we should be aware of, is the interparticulate forces of attraction and repulsion. Just as there are intermolecular forces, there are interparticulate forces as well. At its smallest size, a particle is somewhat indistinguishable from a molecule. A particle is essentially the consolidation of a few molecules, right? So many of the phenomena that apply to molecules will also apply to particles, and one of them is this physical forces of attraction and repulsion between neighboring particles. Now when of course these are known as van der Waals forces, and when two particles come close together, so they set up a potential field between them, which is called the Lennard-Jones potential or the 612 potential, in which the the repulsive portion of this force goes as 1 over r power 6, where r is the distance of separation between the two objects, whereas the attractive force goes as 1 over r to the power 12, and of course they have opposing signs. So basically what happens is, as two particles come close together, they tend to repel each other. When they move farther apart, they tend to attract each other. So you can imagine that in such a situation eventually they will reach a dynamic equilibrium where this potential energy reaches a minimum value, and that is the distance of separation at equilibrium between the two solid objects. These could be two particles, or it could be a particle and a surface, or it could be two surfaces, but they all have the same type of repulsive / attractive behavior between them. And I am sure you have seen these potential energy curves that show this type of behavior. So this is the distance of separation between the two objects, and due to the balancing between the attractive and repulsive forces, the potential energy eventually reaches a minimum, and this depth of this potential energy well is an important parameter because it describes the strength of the interaction between the two surfaces. Basically, the deeper this energy well, the greater is the interaction between the two objects, and of course epsilon then scales with surface energy. Just to relate it back to the discussion we had yesterday, there is a strong relationship between surface energy and the depth of this potential energy well. Of course, the other important parameter is this distance of separation at equilibrium. The smaller the value of d0 is, obviously the more closely the two objects can approach each other. So what does that imply? It implies that the attractive force between the two particles is much stronger than the repulsive component. So again you can see the link to surface energy. The higher the surface energy, the smaller will be this equilibrium distance of separation at dynamic equilibrium. So while this describes the general behavior of the interparticulate forces, the actual magnitude of the epsilon and d0 values are determined by parameters such as surface energy and the Hammaker constant that we mentioned yesterday. So, that is a linking factor. The other important behavior of a particle that is immersed in a medium, as I mentioned in the last class, is absorption/adsorption behavior. Now, absorption of course refers to take up of liquids by a solid, and it is really not a surface phenomenon, because when a particle is absorbing water, the mechanism is not simply building up a layer of molecules on the surface. The subsurface soon gets flooded by the liquid through a wicking process. So, absorption as a process is very different from adsorption. Adsorption in many cases is purely a surface phenomenon. In fact, I am sure you are familiar with the Langmuir adsorption isotherm. Have you studied the Langmuir model yet in any of the classes? Okay. So, the Langmuir model says what? There are three basic assumptions in the model, right? It says A, there is only a monolayer adsorbed. So, you cannot have one layer of adsorbed molecules sitting on top of another layer. It is a single layer of adsorbed molecules. The second assumption is there is no interaction between adjacent adsorbed molecules. And the third assumption is that all sites on the surface of the particle have an equal likelihood of adsorbing a molecule. So, there are no preferential sites on the surface that can take up molecules to a greater extent. So, when you make these three assumptions, that is the basic premise of the Langmuir model. And of course, I am sure you have all seen the graph which plots pressure versus an adsorbed number of molecules, and the general behavior of this is kind of looks like this, right. Now, you can actually derive this from first principles. The Langmuir model is based on the simple assumption that the rate of arrival of molecules is equal to the rate of desorption. So, it is a dynamic balance model. So, if you define certain parameters, let us say that Na is the number of arriving molecules, and let us define a sticking coefficient, because not all molecules that arrive are going to want to stay on the surface. Some of them might bounce off. So, the sticking coefficient is an important parameter. And then you have F. You can look at F as a fractional coverage of the surface by the adsorbed molecules. And finally, you can define a R subscript DES, which is the rate of desorption. Okay. So, based on these definitions, you can quickly write a balance, right, for rate of adsorption to rate of desorption, which would simply say Na times Fs times 1 minus F equals F times R desorption. So, from this you can actually derive an expression for F in terms of the other parameters, and that would look like Kp by 1 plus Kp, where K is a constant that incorporates terms such as the desorption rate and the sticking coefficient. The arriving rate is related to pressure. As you can imagine, the higher the pressure, the greater will be the incident flux of molecules onto a particle surface. So, Na is incorporated in the P term, and when you plot this, actually sorry, this should be F, not Na. So, when you plot this, this is the kind of behavior you get. F will tend to 1 at extremely high pressures, and of course, it will tend to 0 at 0 pressure. Now, so what this is suggesting is, if you have an application, for example, fluidized beds, where the process efficiency depends on adsorbing molecules onto a catalyst surface, pressure is one of the variables that you can play with. So, you should try to operate at a pressure that can get you up over the hump, but at the same time, clearly the relative effect of pressure drops as you keep increasing the pressure. There is an optimum pressure for operation of any system that involves gas adsorption on a solid surface, and you have to find it. So, this is a fairly simple model. So, the Langmuir adsorption is something you should be able to derive based on first principles. But what if you relax the assumption of monolayer adsorption and allow for multilayer adsorption? What is that model called? Anybody has an idea? It is called the BET model. BET stands for Brunauer, Emmett, Teller. The BET model differs from the Langmuir model, which is this one, only in that one respect. It allows for multilayer adsorption. All the other assumptions that I mentioned earlier still hold true. So, in the BET model, of course, the first differentiator is now you are talking about 3D adsorption, because adsorption is not happening not only on a surface, but can also occur above the surface. So, as soon as that happens, you really cannot talk about fractional coverage anymore, because fractional coverage may be 1, but that may be only single layer of adsorbate. For the same fractional coverage of 1, you can have many layers of adsorbate, right. So, the same fractional coverage can be related to many different values of total volume of adsorbate. So, the critical parameter here that you track is not F, but V adsorbed, the total adsorbed volume of the gas onto the surface. So, this V adsorbed can then be related to a parameter that is just like here you are relating this to total pressure P. Here the V adsorbed is a function of parameter X, where X is P by P0, where P is the prevailing vapor pressure of the adsorbed molecule, and P0 is the saturation vapor pressure of the adsorbed molecules. So, V adsorbed is related to X, and the equation that relates to them can be written as Kx by 1 plus x times 1 minus Kx, and the behavior, if you actually plot it, is very different from the Langmuir behavior. Now, the actual dependence is not unique. In fact, different particles can have different behaviors. So, here in the BET model, if you plot V adsorbed versus X, supposing you only have a monolayer of adsorbate, right, then obviously it should still look like this, which is the Langmuir model. However, when you have multilayer adsorption, what does that mean? In its simplest sense, it could still be that the fundamental process is still same as the Langmuir process, but it just happens to a larger extent. So, this could be for 1 layer, 2 layers, 3 layers, 4 layers. So, the fundamental mechanism of vapor uptake does not change, it is just that you keep adding more and more layers, and as you add more layers, V adsorbed keeps increasing as the number of layers increase. Now, but the BET model also allows for fundamental changes in the mode of vapor take up by the particle. When you say monolayer adsorption, clearly you are only allowing the surface to participate in the adsorption process, but vapor adsorption can also involve the subsurface. So, initially adsorption can occur just on the surface, but eventually the adsorbate can start diffusing into the subsurface region, and that can increase the uptake of vapor by the particle. So, for example, initially you may start with something like this, which is the first adsorption on the surface of the particle, but then once the subsurface becomes involved, you can actually have a change in slope, and all of a sudden you may jump to another level of adsorbed material. And as you can imagine, even the core can get involved in the adsorption process if the adsorbate has sufficient diffusivity that it can actually penetrate the surface and the subsurface and get to the core. So, you can even have a third spike. So, you can actually go through 3 different asymptotic behaviors and with a time delay, because initially adsorption can only occur on the surface, and then the subsurface starts participating, and then the core starts participating. So, that is another behavior that is possible in the BET model. Another type of behavior that occurs, see, so far we have been assuming what? Physisorption, right? There is no chemical interaction involved. We are simply saying that the surface is available for uptake, and wherever you have an empty site, particles can stick there, get absorbed. But if you have chemisorption as a mechanism, then in addition to the physical mechanism of interaction, there is also chemical interaction happening. So, as you can imagine, chemisorption is much stronger than physisorption, because physisorption is a reversible phenomenon. An adsorbed molecule can always be desorbed, but chemisorption need not be. In fact, most chemisorption phenomena are irreversible. So, the uptake, the net or equilibrium uptake can be much greater in chemisorption, because the desorption rates are much lower. You can look at net take up as adsorption rate minus desorption rate, right. So, in chemisorption, adsorption rates are high, desorption rates are low. So, automatically the adsorption or the V adsorbed at equilibrium takes up a much larger value. So, in the case of chemisorption, you can again start with something like a physisorption behavior, but it can quickly start jumping to a much larger value once chemisorption kicks in. Chemisorption may also occur right from time 0, in which case you will quickly reach this high level and asymptote out. So, the BET model tries to capture vapor uptake by the particle in all its complexities, and in fact the parameters in the equation can be tuned to capture these various complexities as well. Okay, so that was just a very brief description of adsorption. So, we have kind of looked at three interfacial characteristics: surface energy, intermolecular or interparticle forces, and adsorption behavior. These 3 again are particularly crucial to understanding mechanical operations. So, it is good to spend some time reading and understanding these phenomena. We will now switch to other aspects of particle behavior that also have some important consequences for how they behave in dynamic systems. In particular, the adhesion of particle to a surface and the cohesion of particles to each other are very crucial phenomena. The difference between adhesion and cohesion in a classical sense is adhesion is the sticking of a particle to a much larger surface. For example, if you have a flow of particles or a suspension through a pipeline, so let us say you are pumping some slurry through a pipe, then the attachment of the particles to the surfaces of the pipe is referred to as adhesion, whereas if the particles themselves stick to each other during their flow, that is called cohesion. Adhesion and cohesion have a lot of implications for chemical process industries involving particulate material. Obviously, for the most part they have to be avoided, because when you talk about adhesion, frequently it results in loss of material. As you are flowing something through a pipeline, you do not want the material to stick to the walls of the pipe and get lost from the flow. You want all the material to flow through the pipe. Cohesion again is not good because it can increase the aggregate size of the particles that are flowing in the system, and as that increases, the pressure that is required to drive the same flow rate will keep increasing as well. So, you can imagine that in the most extreme case, if there is very extensive cohesion, a suspension may actually eventually start behaving like a solid block because all the particles are stuck to each other. So, you are trying to drive this big boulder through the pipe rather than individual particles. So, in most flow equipment in chemical process industries, mechanical operations that involve particulate flow, you want to minimize both adhesion and cohesion. Now, there are obviously applications where they can be of use as well. For example, sometimes particularly in sampling for measurement, you are trying to collect particles through an adhesive mechanism. We talked about isokinetic samplers, which basically rely upon the fact that particles will actually stick to a surface so that they can be sampled at a later time. There you want to maximize adhesion, but those are exceptions. In most cases, remember that in mechanical operations, you want to minimize adhesive behavior and cohesive behavior. Cohesive behavior, by the way, is also of importance in silos where large quantities of material are stored. Now, in a silo, what you want to do is periodically you want to open the door and remove some material for use in your process. Now, in that case, is cohesion good or bad? Actually, in terms of discharge from silos, cohesive behavior is considered to be better because it is more predictable. If you do not have cohesive behavior of stuff that is stored in a silo, then it is very difficult to withdraw the same amount of material every time by keeping the door open for the same amount of time. So, that is another application where cohesive behavior is actually to be encouraged. So, we will just try to understand the basics involved in adhesion and cohesion, and then we will talk about their relevance as we talk about individual processes and applications. So, first when you talk about adhesion, there are many mechanisms of adhesion. The simplest one is again the van der Waals forces of adhesion, just due to intermolecular interactions between adjacent particles, between adjacent surfaces, and so on. But another mode of interaction which is quite dominant is when you have electrostatic forces and electrical forces in general involved, which is all the time, because when you look at particles in the atmosphere, very frequently they are charged. There is a charge distribution. It is in fact very difficult to find a particle that contains no charge, and the amount of charge buildup scales as roughly particle size. So, larger particles tend to carry more charge than finer particles. So, any interaction between two particles is also influenced by the charge buildup on these particles. So, when you talk about adhesive forces, we can classify them as 5 major types of forces. The first is the simple van der Waals forces of physical interaction. The second is the electrical forces. So, you know about Coulombic forces between adjacent bodies. There is something known as an image force and contact potential forces. And there is also an ionic double layer force or the zeta potential. And then you have the surface tension based forces. which are also known as steric forces. The fourth type is hydrophobic hydrophilic forces. And finally, we just call them special forces. The first four are universal forces. They apply to all classes of particles. But there can be special forces that apply for certain types of particles. For example, if you have magnetic particles, then magnetic force fields will apply. Or if you have a process in which you are trying to sinter a material, then sintering forces can become a force of adhesion. Physical interlocking, if you have special features on a surface and a particle that allows them to interlock with each other, that's another kind of adhesive force. Or even the chemisorption or chemically reactive forces that we talked about earlier is again a special kind of force, because it does not apply to all particle classes, but there are certainly many particles that can interact with each other chemically or with the surface chemically and form a chemical bond. So, chemical bonding forces are also to be considered as a special case, but the first four apply, as I said, virtually to any system involving particles and surfaces. So, van der Waals force, as I mentioned in the last class, it is related to a parameter called the Hamaker constant, which is in essence a sum of all interactive forces between the molecules that comprise adjacent particles, right. So, the van der Waals force of adhesion is proportional to the Hamaker constant for the system. Now, when we talk about interaction between particles or particles on a surface, we have to remember that it is a three body problem. So, you have a particle and you have a surface, or let us say another particle, but you also have an intervening fluid medium between them. Unless it is a special case where everything is occurring in vacuum, there is always an intervening fluid between two interacting solid bodies. So, the forces of adhesion between the particle and the surface depend also on the properties of the intervening fluid. So, let us say that you call this 1, this 2, and the intervening fluid as medium 3, then the van der Waals forces of adhesion, which are proportional to the Hamaker constant A, actually depend on not the Hamaker constant of 1 alone or 2 alone or 3 alone, but a system Hamaker constant, which we write as A subscript 1 3 2, and this Hamaker constant for the system depends upon the Hamaker constants for the individual bodies that are involved. So, it will depend on the Hamaker constant of material 1, the Hamaker constant of material 2, and the Hamaker constant of material 3. So, the exact dependence you can refer to the lecture on this topic in my particle characterization course, but it is important to remember that you have to look at it as a system, and the intervening fluid, by the way, plays a huge role. If you look at the A132 value for where the intervening fluid is air compared to where the intervening fluid is water, and you take the ratio. So, if you take the ratio of A132 where 3 is water divided by A132 where 3 is air, that ratio can be of the order of 100. In other words, van der Waals adhesion forces are much weaker when a surface is immersed in water compared to when it is in air. That is kind of intuitively obvious, right? When you are trying to wash dishes, what do you find? When you soak them in water, they become much easier to clean, right? And the reason is that, well, there are a few different reasons, but one of the reasons is when you immerse the interface between a particle and a surface in water, the Hamaker constant, which dictates van der Waals forces, is reduced by 2 orders of magnitude, making the particle much easier to dislodge from the surface. So, so the Hamaker constant itself depends on the properties of the particles in the fluid, but the adhesion force, the van der Waals adhesion force, is proportional not only to A132 but also the shape of the particle. You know, shape interestingly plays a very strong role in determining adhesion between two particles or between two particles and a surface, I mean between a particle and a surface. In other words, how a spherical particle will adhere to a surface is very different from how a cylindrical particle will adhere to a surface. So, shape plays an important role, and of course, the distance of separation between the particle, between two particles or between a particle and a surface. As you can imagine, the closer the distance of approach, the greater will be the adhesive force, as we have seen before. And finally, the van der Waals force will also depend on the properties of 3, the medium in which this system is immersed. So, just to give you a feel for how these differences are, in the simplest case, let us say you have a spherical particle on a surface, and let us say that the particle diameter is some dp and this distance is z0. The force of van der Waals adhesion in this case goes as dp squared, and it goes as 1 over z0 squared. Sorry, it goes as dp and 1 over z0 squared. In other words, the force of adhesion is, in the case of a spherical particle, directly proportional to the particle diameter, and it is inversely proportional to the distance of separation between the particle and the surface. It is kind of the classical case. This is how we would expect adhesion to happen. But if you look at a cylinder, let us say that you have a cylindrical particle, some length L and diameter dc, which is again near a surface, and again the distance of separation is z0. In this case, the van der Waals force actually goes as dc to the power half and 1 over z0 to the power 2.5. So, the dependence on the diameter of the material as well as, and this is per unit length, by the way, this is the adhesion force per unit length of the cylinder. Both the exponents are different. Let us look at a third case where you have two surfaces that are in contact, again separated by a distance z0. In this case, obviously there is no diameter dependence, but the dependence on the distance of separation goes as z0 cubed. You might have seen these experiments. If you bring two extremely smooth surfaces together, the force of adhesion between them can be infinity. You can never separate them. In principle, it is infinity. And the reason for this is this kind of behavior. When you have two surfaces that are being brought together, the force of adhesion between them scales as 1 over cube of the distance of separation between them. So, clearly the smoother the surfaces are, the closer you can bring them. If you have a rough surface, the height of the roughness asperity limits the closest distance of approach, right? Whereas, if you have a finely polished surface where the roughness is of the order of nanometers or less, in principle this z0 value can be extremely small, and that can result in extremely high adhesion forces. All right, so this is how particle adhesion happens, and we have kind of looked at the two limiting cases, one a spherical particle and one is a cylindrical particle, but you can imagine that the actual adhesion force will depend on the aspect ratio or the ratio between the longest dimension and the shortest dimension, and the but the exponent of the distance of separation will only vary between 2 and 2.5, because we have looked at the two limiting cases of spherical and cylindrical, and the exponents are 2 and 2.5. So, you can imagine that for particle shapes that are between sphericity of 1 and sphericity of virtually 0, the exponents will be of the order of somewhere between 2 and 2.5. And the assumption that we have made here, there are a couple of assumptions in this model. The first is that we have assumed that roughness is not a critical parameter. We have assumed that the adhesion behavior can be predicted based upon the macroscopic distance of separation between the surface and the particle. But in reality, what is going to happen? You will never have a smooth surface, right? It won't look like this, it will actually look like this. So, in the case of adhesion, what effect that does roughness have? In general, do you think roughness will increase adhesion or decrease adhesion? How many think a rough surface will be less adherent than a smooth surface? How many think it's the other way around? Rough surface. How many have no opinion? Think about it. I want everyone to vote. How many think that adhesion will be stronger on a smooth surface? Okay. How many think it will be stronger on a rough surface? Okay. Can I have one opinion from the smooth team? Why do you think a smooth surface will have more adhesion?
Because they can come closer.
Yeah. It will come closer, okay. And from the rough team, any? Okay. So, actually the answer is both. You cannot say one way or the other. It depends on the difference in the roughness between the particle and the surface. In fact, one way to look at it is if you have a particle whose diameter is larger than the typical roughness element, then the particle is going to sit on top of the roughness asperity, which will minimize the area of contact between the particle and the surface. So, a large particle approaching a rough surface is almost always going to be less strongly adhered compared to a large particle approaching a smooth surface. However, if you have fine particles, let us say that you have particles in the submicron size range or the nano size range, it is quite possible that the particle may actually be smaller than the width of the roughness asperities, in which case the particle can actually nicely nestle within this, and actually the particle will be much better adhered now compared to on a smooth surface. So, it is certainly possible that fine particles will have a different behavior based on roughness compared to large particles, and of course, the interlocking is another possible mechanism. If you have a rough particle approaching a rough surface and the roughness distribution is such that they can actually provide an interlocking, you can see evidence of stronger adhesion of the particle to the surface. But in general, if you talk to people in industry, like for example people managing pipelines, and they want to minimize adhesion to the surface, they will say a rough surface works much better. They would want to avoid a smooth surface, because smooth surface results in buildup of a lot more material than a rough surface. In fact, one of the standard treatments that is done to minimize things like fouling of heat transfer surfaces in power plants is roughening the surface. Even glass, glass buildings have a tendency to pick up dust and dirt. So, if you talk to people in the civil industry about how they would minimize dust buildup on glass, they will tell you that one of the treatments that they use is roughening of the glass, micro roughening, or now they are looking at nano roughening, which will provide this extremely fine rough finish on the surface, which will prevent dust from accumulating on the surface. So, in general I would say smoother is better, rougher is better to minimize adhesion. The other parameter that we haven't looked at here is what I would call hardness. We are assuming that when the particle approaches a surface, neither the particle nor the surface are deformed. So, you are looking at a hard particle interaction with a hard surface, but in reality there is going to be a relative hardness between the two. Either the particle will be harder or the surface will be harder. What effect will that have on adhesion? Will it in general increase adhesion or reduce adhesion? Reduce. Anybody votes for increase?
Both are hard, the magnitude of force will reduce. So if they can soften the magnitude,
then it will increase. I mean the adhesion will increase, right? So, the correct answer is that if you have a deformable surface, then the forces of adhesion will be greater, and also there will be a time dependence. When you have hot particle hot surface interaction or two hot particles interacting, then the time 0 behavior will be the same as the long term behavior. The adhesion force will not change significantly over time. But you can imagine that if you have a surface that is deformable and you have a particle approaching, initially it may be a hard surface type of interaction, but what will happen over time is this will start deforming to accommodate this particle, and eventually the particle will be much better integrated into the surface than at time 0. So, the force of adhesion as a function of time will keep increasing. Also, hardness has a direct role to play in terms of determining the Hamaker constant. In general, the harder the surface, the greater will be the Hamaker constant. So, metals and alloys have the highest Hamaker constant values. The softer metals like aluminum, magnesium will have a lower Hamaker constant. Plastics, hard plastics will have a Hamaker constant that is lower than soft metals. Soft plastics will have a Hamaker constant that is lower than hard plastic, and finally elastomers will have a hardness or a Hamaker constant that is lower than soft plastics. So, there is a gradation in the Hamaker constant depending on the hardness of the material, which correlates with the surface energy of the material. So, this again goes back to our discussion in the last class, that if you want to reduce adhesion of a particle on a surface due to intermolecular forces, then providing a lower surface energy finish to the material helps in terms of reducing the force of adhesion. For example, Teflon will have a much lower surface energy compared to stainless steel, and therefore it will have a much lower Hamaker constant, and therefore it will have a much lower van der Waals force of adhesion. So, by using Teflon coating, you can effectively prevent van der Waals forces of adhesion or adhesion phenomena from happening. However, it may result in an increase in other forces of adhesion. You always have to think about adhesion as a net process. It is not just that one mechanism is going to control the rate of adhesion. It is going to be a combination of factors. We listed some of them here. So, for example, something you do to a surface may reduce van der Waals forces, but it may increase some of these forces. Then the net effect is actually going to be worse. So, you have to learn to look at particle adhesion to each other and to surfaces in a holistic way, and understand the implications of any change that you make to the process. Right? You do not want to sacrifice something for gaining something, or even if you do, you have to make sure that the trade-off ultimately helps you rather than hurting you. So, in the next class we'll discuss the remaining mechanisms of adhesion, and then we'll start talking about cohesion. Again, all this material is in lectures 13 onwards in the NPTEL course, and I'm trying to cover couple of 2 or 3 lectures in each of these lectures. So, you'll have some catching up to do. So, hopefully you'll be able to do that, and by Thursday. Any questions? Okay, so see you next class.